Alright, so this is the review for the last test. And I took basically 9 days to lecture on this chapter, maybe a little bit less than that. And the stuff at the beginning already kind of feels like I haven't done it forever. So if you took 2 or 3 weeks to go through this chapter, you might want to review a little bit before looking at this review, just because it might feel new again. And you kind of want to do the review, you know, even before watching the video. Kind of treat it like a test. If you could do all the problems on the review, you should be able to do all the problems on the test. So problem 1 is an empirical probability problem, and it says 1,000 Ford F-250s at random were tested. 15 of them had some sort of cosmetic defect. Determine the empirical probability that a truck had a cosmetic defect. Well, it's just the 15 that had cosmetic defects out of the 1,000 that were tested. And more or less for every probability question, we wrote our answer as a reduced fraction. So I'm going to write this as a reduced fraction. So I'm going to go 15, let me just clear this out, 15 divided by 1,000, math, enter, and you get 3 out of 200. I've literally been teaching or doing videos in this room, I don't know, this room's about 6 years old, so probably 6 years. And I think I finally figured out where to put my calculator to make it not have a glare. I always had my paper over to the right just because it's easier for me to write, but I discovered at the end of the last video, if I move my paper over to the left, I can get the calculator on there where you can still see a little bit and not have a glare. It's kind of nice. So part B of this, if 100,000 F-250s are being produced, how many of them will have a cosmetic defect? It's just the percentage or the fraction of them that will have a cosmetic defect times the total number produced. And when I do this, I'm going to do it in a parentheses just to be safe. I'm not sure if I don't put the fraction in a parentheses whether it will or won't think of the 100,000 as being in the numerator or not as part of a denominator. Really? Not like, oh, it's supposed to be times, idiot. It's supposed to go parentheses 3 divided by 200 times 1,0,0,0,0, and I get 1,500 of them. So it would probably be nice if I took some words with the numbers, or wrote some words with the numbers, but I'll live with just the number. I should be in the habit of checking every answer that is checkable. So I know I printed out the answers, but of course I didn't bring the answers that I printed out. So I'm going to roll the dice and hopefully I don't make a mistake. I have made a mistake on a review video before and took the time to redo the whole thing. Hopefully I don't make any mistakes this morning. Okay, so this is a theoretical probability question. Remote control has channels for 0 through 9, or keys for channels is a week, but numbers 0 through 9, which are 10 different numbers. And then you're going to pick one key at random. So the denominator, if you pick one key at random, is going to have a denominator of 10, because this remote control has 10 different number buttons or digit buttons that you can select. The numbers 1 through 9 and 0. If you press 1 at random, the denominator is going to be 10 because you can get any of the 10 buttons if you randomly press. And then for do not press the number 6, I need to count all the numbers that can be pressed that fit do not press the number 6, and that's all 9 of the numbers other than the 6. For part B of this, the denominator, if I'm pressing one key, is going to have a 10 in it because there's 10 different numbers I could press. The numerator is going to have the numbers that are greater than 4 because that's the requirement here. There's 1, 2, 3, 4, 5 numbers that are greater than 4. So I'm just taking the items from the sample space that fit the criteria, putting that number in the numerator, and 5 and 10 reduces to 1 and 2. So we had a couple different problems in the chapter with Mississippi. We had a problem that was a distinguishable permutation problem. That's way later. It's not yet. Here, I'm just taking the letters from Mississippi, putting them on individual sheets of paper, putting those individual sheets of paper in a hat, and randomly picking one of those sheets of paper out. And now I want to find some probabilities. And if I'm picking one letter from my hat that has those letters from Mississippi, 1, 2, 3, 4, can't spell Mississippi, Mississippi, getting to be moronic. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The denominator for both of the probability questions in question 3 will be 11 because I'm picking one of the 11 letters the numerator is going to be the number that have the desired choice, and in part A, the desired choice is there an S. So that's going to be 4 and 11. For part B, I want an I or an S. We learned how to do OR probabilities with formulas, and the formula is important if there is kind of overlap. If there were letters that were both I's and S's simultaneously, then I would need the formula to do the problem. But in this case, because the I and the S's are they're distinct letters, I don't have to worry about the formula. So I marked all the I's and the S's, which is most of the word. If I count up all the I's and the S's I have marked here, that's 8 of the 11 letters. So the probability of picking an I or an S would be 8 and 11. All right, we have a box of marbles, and we're doing odds. So for odds, it makes a difference if it's odds against or odds in favor. Part A of number 4 is an odds against. Part B of number 4 is an odds in favor. So if I'm doing the odds against getting a red marble, I need to make essentially 2 piles of marbles for problem 4, and the first pile needs to have all the marbles that are not red because I need to count them up, and the second pile will have all the red marbles. So when we do odds, we split the sample space into those that don't have the desired characteristic and those that do have the desired characteristic. When it's against, those that don't have the desired characteristic go first, and when it's for, those that don't have the desired characteristic go second. So in this problem, the not red marbles are the 2 blue and the 3 yellow, and the red marbles are the 9 red. So the odds against selecting a red marble are going to be 5:9 for the 5 not red marbles and the 9 red marbles. For part B, we're doing odds in favor of selecting a blue marble, so I need to separate the marbles into not blues and blues, and because it's odds in favor, the nots come second. So I'm going to separate into blue and not blue. So for the blue, there's just 2 blue. For the not blue, there's 3 yellow and 9 red. So the odds in favor of selecting a blue marble would be 2:12. This, if it was a fraction, 2/12, it would reduce by 2. And I consistently don't usually reduce odds, but the answers that I showed in the section, I think, had both non-reduced and reduced. So if you reduce, it's fine, because we reduce probabilities. Why wouldn't we reduce odds? So both of these answers would be okay. All right, a little bit harder to do odds with cards. So each one of these from 5 to 7 wants me to do odds against. So I'm going to have the not that card and then are that card. For 5, I have to break up a deck of cards into those that aren't hearts and those that are hearts. The not comes first because it's odds against. Now I know that there's 13 hearts. If you went to my deck of cards, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So on the side that asks me for hearts, I need 13. I don't want to count all the non-hearts, so to get the non-heart side, a deck of cards has 52 cards. If I subtract out the 13 that are hearts, then the rest of them are not hearts. So it would be completely okay if I wrote 39:13 for an answer, and if I reduce that by 3, 39 divided by 13 is 3 if I reduce by 13, and 13 divided by 13 is 1. So you could, you don't have to, but you could divide both of those by 13, and that would give me a 3-to-1 odds. For problem 6, I need to break my deck of cards up into those that aren't 7s and those that are 7s. The not is first because it's odd against. If it was odds in favor, it would be 7s, and the not 7s would be second. In a deck of cards, there are 4 7s. So on the side that wants me to count the 7s, I'm going to put 4. And then for the side that wants to have not 7s, I'm going to take the 52 total cards, subtract out the 4 7s, and get 48. So this would be a completely good answer, or I can divide both of these by 4. And if I divide them both by 4, I'd get 12-to-1. Somehow that almost looks like a better answer, but I'd live with both of them. And for the last one of these, I need to separate the deck into not black cards and are black cards. And then the not black cards are all the red cards. And so all the hearts, which are 13 of them, and all the diamonds, which are 13 of them, are the not black cards. So there's 13 hearts plus 13 diamonds. There's 26 cards in the deck that classify as not black. If they're not black, they're red. So for the not black side, I'm going to put 26. And for the other side, I'll take the well, there's 26 black cards, but I would take the 52 total cards minus the 26 that aren't black, and that will give me 26 that are black. So this would be an acceptable answer, or you can divide both of these by 26 and get 1:1. That was section 4.2. So we're probably moved on from section 4.2 and we'll move into section 4.3 now, I would guess. Yes. So a couple plans to have 2 children, and we're going to eventually be asked to make a sample space that has boy, girl, girl, boy kind of thing in it. And the number of points in the sample space you get by using the counting principle. You're going to make 2 dashes, 1 for each kid. And above those dashes, you're going to write the number of possibilities. Well, for the first kid, there's 2 possibilities. It can be a boy or a girl. For the second kid, there's 2 possibilities. It can be a boy or a girl. So my sample space, when I list all the possible orderings of 2 kids, having boys and girls listed in all the possible orders, there's going to be 4 elements in the sample space. Part B wants me to actually construct the sample space. To construct the sample space, I start off making room for the first kid. First kid could be a girl or a boy. And then I make room for the second. And the second kid can be a girl or a boy as well. So this G right here represents getting a girl for the first kid and a girl from the second kid. This B right here represents getting a girl first and a boy second. This G right here represents getting a boy for the first kid, a girl for the second, and this B is getting a boy first and a boy second. So that's end of part 2, and each of the probability questions I'm going to have a denominator of 4 because there's 4 elements in the sample space, and I don't see the word given that anywhere, so I don't need to create a reduced sample space. So for part C, as well as part D, I'm going to put a 4 in the denominator. For part C, I want to count all the items in the sample space that have more than one girl to get the numerator. And for part C, the only item I'm going to count is the double G, because that's the only one that has more than one girl. So the numerator will be 4. For part D, I want to count the ones that have a boy and a girl, and that are those two. The second and the third items in my sample space have one boy and one girl. So that's going to be 2 and 4, and probabilities, we show them as reduced fractions. So that's going to be 1 and 2. Coin is tossed 3 times. So for probability purposes, coins and kids work the same way. So to do part A, the number of items in the sample space, I'm going to make a first toss, or a first flip, a second flip, and a third flip. And each time I flip it, it can come up heads or tails, so there's 2 different possibilities. And if I multiply those 3 2's, that will tell me my sample space is going to have 8 elements in it. For the first flip, I could get a head or a tail, so that's the first. And then for the second, still get a head or a tail. And then as I do the third, I'm going to create the sample space just because these things get kind of messy. So for the third, I can get a head or a tail. To get to this head right here, you would have had to gotten a head first, a head second, and a head third. So the first item I'm going to write in my sample space is head, head, head. I didn't take the time to write it in set notation. Last time I just listed it out here, and this time I'll write it a little bit nicer, like you might want to write it on a test, I guess. On the last problem, for the sample space question, I probably should have said sample space equals girl, 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 boy, boy, girl, and boy, boy. There's on the test, there's going to be a slot to write your answer, and it's probably nice to write it in with naming the sample space using set notation. But if you don't, if you just get the right elements, I'll let it. Getting back to this, I need to march to this T, and that would be getting a head first, a head second, and a tail third. Now I'm going to finish up this branch, adding a head and a tail. To get to this head, it's head first, tail second, head third. And then to get to that tail, it's head first, tail second, tail third. The slick thing to do right now is just to take these 4 elements in the sample space, copy them again, and change all those heads to tails. That will work every time, so, but I won't do that, but you can. So now I'm going to keep going on the lower part of this. To get to this head, it's tail, head, head. To get to this tail, it's tail, head, tail. Finish up the last branches. To get to that head, it's tail, tail, head. And to get to that tail, it's tail, tail, tail. So it would be nice if I said sample space equals, and I wrote head, 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 comma, head, head, tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, and tail, tail, tail. Using S for the name, putting them in set brackets would be nice. So when I go to answer the probability question in part C, because there's 8 elements in the sample space, my denominator is going to be 8. And then the numerator needs to find out anything in the sample space that fits the criteria that exactly one head is drawn. So that's 3 heads, that's no good. 2 heads, 2 heads, there's 1 head. 2 heads, there's 1 head, there's 1 head, there's no heads. The 3 things that I just highlighted, they're the only 3 things in the sample space that have exactly 1 head. The other ones have 0 heads, 2 heads, or 3 heads, and they don't count in when I'm trying to find exactly 1 head. So for part C, my answer is going to be 3 and 8. All right, so this is a probability question that's an OR question. And to do the probability of an OR, we used a formula. So I'm going to continue to use that formula. So this is moving on to the, oh gosh, this is section 4.4 now, I suppose. So I want to find the probability of getting an odd number or a number less than 4. And that's going to equal to the probability of getting an odd number plus the probability of getting a number less than 4 less the probability of getting an odd number, a number that's both odd and less than 4. So now I'm going to mark up my sample space. I'm going to create a sample space. And when you roll a single 6-sided dice, the sample space is just any one of the 6 numbers. And now I'm going to mark the odd numbers. So the first fraction is going to have a denominator of 6 because there's 6 elements in the sample space. The numerator is going to be 3 because there's 3 odd numbers. The second fraction, I'm going to box the numbers that are less than 4. 1 is less than 4, 2 is less than 4, 3 is less than 4. So that's also going to have a 3/6. The last fraction, anything that's marked for both scenarios needs to be subtracted out. The 1 and the 3 are the elements that fit both criteria. They need to be subtracted out into the probability of getting a number that's odd and less than 4. Now I'll just reduce this. This is 3 plus 3 minus 2/6. And that's got to be 4/6. So my answer to number 10, the probability of getting an odd number or a number less than 4 is 2 and 3. 11, I'll write it up the same way. It's the probability of getting a number less than 3 or greater than 4. That's going to equal to the probability of getting a number less than 3 plus the probability of getting a number greater than 4 less the probability of getting a number that's both less than 3 and greater than 4 simultaneously. So now I'm going to create a sample space and mark it up. For the first probability, getting a number less than 3, that only counts the 1 and the 2, because those are the only numbers that are less than 3 but not equal to 3. So the probability of rolling a number less than 3 is 2/6. There's 6 elements in the sample space. There's 2 that fit that criteria. To get a number greater than 4, that's the 5 and the 6. So there's 2 items in the sample space that work for it. Now I need to subtract out any duplication, and there aren't any numbers that are both oranged out and circled. So it's impossible to roll a number less than 3 and greater than 4 simultaneously. There's no number that fits that category because there's no overlap between those choices. So that's a 0 and 6. So my answer is going to be 2 plus 2 minus 0/6. It's 4/6 again, and that's going to be 2 and 3. So probabilities with hearts, picking 1 card from a deck of cards, same thing. So for question 12, the probability of a queen or a heart equals the probability of a queen plus the probability of a heart minus the probability of getting a card that's both a queen and a heart. So each one of the fractions is going to have a 52 in the denominator, because when I'm picking one card from a deck of 52 cards, there are 52 cards that are possible, and that's what goes in the denominator, the number of possibilities. For my first, I'm going to box out the queens, and there are 1, 2, 3, 4 queens. So for the probability of getting a queen, it's going to be 4 in 52. The next probability I want to do is the probability of a heart, and I need to mark out the heart. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 hearts. So the next fraction, its numerator is going to represent the number of hearts, which is 13. The last fraction, I need to subtract out anything that I've double counted, and that would be the one card, the Queen of Hearts. It's marked for the queens and it's marked for the hearts, so that's the probability of getting a card that's both a queen and a heart. That's going to be 1 in 52. Now I'm just going to do the math. This is going to be 4 plus 13 minus 1 over 52. That's 16 over 52. And let me reduce that. So I'll go 16 divided by 52. Math, enter, enter. I'm going to write 4 and 13 for my answer. To get the probability to get a club or a 4, so the probability to get a club or a 4 is the probability of a club plus the probability of a 4 less the probability of getting a card that's both a club and a 4. I think it's the same answer. So first I want to mark out all the clubs, and there are 13 clubs, so there's ace through king of clubs, so the numerator for that fraction is going to be 13. The denominator is 52, because if you're picking one card from a deck of cards, there's 52 possibilities. The next probability I want is the probability of getting a 4, so I mark out all the 4s. There's 4 4s, so the numerator for that fraction is going to be 4. And then the last fraction that I need to contend with is anything that's double boxed, and that's this 4 of clubs. It's been counted as a 4 and it's been counted as a club, so that's the probability of getting a club and a 4 is 1 in 52. It's exactly the same final answer, because it's going to be 13 plus 4 minus 1 over 52, which is 16 in 52, and I'm going to write 4 over 13 for it. And then for 14, I need to do the probability of a heart plus the probability of a spade less the probability of a card being both a heart and a spade. So I'm going to start off by marking off all the hearts and counting those up. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 hearts. So the probability of getting a heart is going to be 13 over 52. Next, I'm going to mark out the spades. The probability of getting a spade is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 over 52 again. So both of my first two fractions are 13s and 52s. And then I have to subtract out any card that's been counted in both sets. There aren't any overlaps. The hearts and the spades are disjoints. So the next fraction is going to have a numerator of 0. So it's going to be less 0 over 52. So this is going to be 13 plus 13 minus 0 over 52. That's going to come out to be 26 over 52. And I can reduce that without my calculator. That's going to be 1/2 for the answer for 14. And more OR problems. Really loaded up these OR problems. So we have a jar of marbles that has 4 reds, 5 whites, 6 blues, and 2 yellows. I think I did a ton of these problems because historically these aren't the best problems on the test, so I just wanted to hammer them down. So the probability, if you take one marble out, the denominator is going to be 17 because there's 17 different marbles. And now I need to find the probability of a red or a blue, which is the probability of a red plus the probability of a blue less the probability of getting a marble that's both red and blue. For the probability of a red, I'm going to count those 4 red marbles. That's going to be 4 of the 17 marbles. For the probability of a blue, I'm going to count those 6 blue marbles. And for the subtracting part, there aren't any overlaps, so there aren't any things that were counted twice, so that's a 0 over 17. So this is just going to be 4 plus 6 minus 0 over 17. And that turns into the non-reducible fraction, 10 over 17. For 16, the probability of a yellow or a red equals the probability of a yellow plus the probability of a red less the probability of a yellow and a red. For the probability of a yellow, it's going to be 2 and 17. For the probability of a red, it's going to be 4 and 17. And for the last fraction, it's going to be 0 and 17 because there aren't any marbles I've marked twice. So this is just going to be 2 plus 4 minus 0 over 17. And that's a nice non-reducible fraction as well, 6 over 17. Got to be out of the OR sections. Yes. Now we're taking 2 cards without replacement, and I'm going to find out the probability by making 2 fractions, getting the appropriate denominators, and then I'll get the appropriate numerators. So without replacement means for the first card, there's 52 cards to choose from, but it's not being placed back. So once you pull it out, you can't pull it again. And the second card, there's only 51 cards to choose from. So for both 17 and 18, the denominator needs to increment down from 52 to 51 because you're not putting the card back. For 17, the first card and the second card both need to be hearts. So for 17, the first numerator is going to be 13 because there's 13 hearts in a deck of cards. I have to assume that I picked one of those hearts. It doesn't matter which one I assume is picked, but I just have to cancel out one of them. And then when I go to pick my second card, one of the hearts is already gone, so there's only 12 hearts left. There were 13 hearts to start with. I removed one of the hearts. For the second probability, there's only 12 hearts left. Now I'm going to do these on my calculator straight up. So I'm going to go on, clear it out, parentheses 13 divided by 52, parentheses 12 divided by 51, enter, math, enter, enter. I'm going to get 1 in 17 for number 17. For number 18, the first card can't be a heart, so the first card can be most anything. It can be any of the clubs, 13 of those. It can be any of the spades, another 13 of those. That puts me up to 26 cards. And it can be any one of the diamonds. Doesn't matter which one of those I pull. I'm going to pull one of those. There's 39 cards there. 13 clubs, 13 spades, 13 diamonds, 13 plus 13 plus 13 is 39. That's for the first card not being a heart. It doesn't matter which one of those I pull. When I go to get my second card, I want it to be a heart, and I wouldn't have pulled a heart. Regardless of the card that I think I pulled, I'll have all 13 hearts available. of the 51 cards, one less than 52 because I pulled one of the cards out. So the next fraction is going to have a 13 in the numerator because there's still 13 cards left, 13 hearts left in my deck. The denominator is going to be 51 because I removed one of the cards, but I didn't remove a heart. So it's going to be 13 and 51, and now I just break out my calculator. So clear parentheses 39 divided by 52, parentheses 13 divided by 51, math, enter, and I get 13 and 68 for number 18. So this is a with replacement problem, so my denominator is going to be the same each time. So 2 marbles are drawn kind of one at a time. We have 5, 8, 10 marbles in the bag. So when I'm taking 2 marbles out of a bag, I'm going to form 2 fractions, 1 for each marble. And if it was without replacement, the denominators would go 10, then 9. But in this case, the denominators are going to go 10, then 10, because I'm putting the marble back. So for each time that I pick, there's going to be 5 blue, 3 red, and 2 purple. And that's going to be the case both times, so I'm putting any marble back. For the first choice, I need the marble to be blue, and we have 5 blue marbles in that bag. Regardless of which of the 5 blue marbles I pick, I put it back in, there's still going to be 5 to choose from on the second time. So it's both are going to be 5 and 10, and this is going to come out to be 1 and 4. I'll do it on my calculator just so you can see. So parentheses 5 divided by 10, parentheses 5 divided by 10, math, enter. So it's a 1 and 4. For this next one, there are 3 reds, and I need the first one to be red. So the first numerator is going to be 3. And then for the second one, I still have all 10 marbles to choose from. And for the second one, it would be okay to get any of the 3 red or the 2 purple, because I want it not blue. So there's going to be 5 marbles in that bag that classify as not blue. So that's 3 and 10 times 1 and 2. What's that? 3 and 20. So parentheses 3 divided by 10, parentheses 5 divided by 10, enter, no math, enter, 3 and 20. Create a reduced sample space. So this is a conditional probability questions, and on the test I should give you the pair of dice blanks, the complete sample space, so you can create a reduced sample space. So what's the probability when I roll 2 dice that the sum is greater than 10 if, or given the second dice is a 5? So I need to go through the initial sample space and mark out all the ones that have the second dice being a 5. That's going to be my reduced sample space. So it tells me right on the instructions that this is a conditional probability that I need a reduced sample space. So my reduced sample space are going to have those 6 elements. So my reduced sample space would be getting a 1 and a 5, which is a sum of 6, a 2 and a 5, which is a sum of 7, a 3 and a 5, which is a sum of 8, a 4 and a 5, which is a sum of 9, 5 and a 5, which is a sum of 10, and a 6 and a 5, which is a sum of 11. I'm going to use only this sample space to answer question 21. The denominator of this answer has to be 6 because there's 6 items in the sample space that relate to this problem. The numerator needs to be the number of items in the sample space that fit the criteria that the sum is greater than 10. And that's only those. That's the only item in the sample space that has a sum bigger than 10, because 10 is not bigger than 10. For 22, I need the first dice to be a 2. So I'm going to go through the sample space and mark out all the ones that have the first dice as a 2, that's the sample space I'm going to use to answer this question. So the sample space I'm going to use is 2 and 1, sum 3, 2 and 2, sum 4, 2 and 3, sum 5, 2 and 4, sum 6, 2 and 5, sum 7, and 2 and 6, sum 8. So that's the sample space that works for this problem. The denominator for this question again is going to be 6 because there are 6 items in the sample space. The numerator needs to be the ones that have even sums, and that has an even sum, that has an even sum, that has an even sum, because 4, 6, and 8 are even numbers. 3, 5, and 7 aren't even numbers, so I didn't circle those. So this is going to be 3 and 6, which is a half. Sum is greater than 4 given the first dice is a 1. So the sample space I need for it is the items here that have the first dice a 1. So the reduced sample spaces I need for this are 1 and 1, sum of 2, 1 and 2, sum of 3, 1 and 3, sum of 4, 1 and 4, sum of 5, 1 and 5, sum of 6, and 1 and 6, sum of 7. So the denominator again is going to be 6 because in the sample space that works for the criteria here, there's 6 elements. I need the sum greater than 4. That's that, and that. Each of those sums, 5, 6, and 7, are greater than 4. So the numerator is going to be 3, and that's going to reduce to 1/2. All right, so more conditional probability questions, and we're basically just going to line out one row or one column and look at it. And for problem 24, the important part is the child's a girl. So the only part of the sample space I'm going to look at to do problem 24 is the part where the child's the girl. This should say 24 to 25. It shouldn't say 24 to 26. Fix that. So for my denominator, I'm not going to look at any other part of the table, any numerical part of the table, except the ones that fit the child as a girl. So the denominator for this probability is going to be 160 because that's the total number of girls. The numerator needs to be within the row the ones that fit the desired characteristics, and the desired characteristic is the child selected the elephant, and there's 85 of those 160 that fit that. So now I'm going to go 85 divided by 160, and then math, enter, enter, and get 17 over 32. For question 25, I go through and I read the problem. I need to figure out the part of the sample space or the part of the column of, or row of numbers that I need. And here it said the child preferred the lion. So these are the numbers that I need, and I'm going to ignore all of these. It won't make a difference. The denominator for my probability question is going to be 165 because that's the total of this column. Now I go to before the word given, it says the child is a boy. Among the highlighted data, there's 90 boys that are featured. So it's going to be 90 over 165. Already fighting myself here. Math, enter, enter. So I'm going to write 6 over 11 for my answer. How many combinations? So I have a lock that has 31 different numbers on it. It has the numbers 1 through 30 and 31. So there's 31 numbers, and it's probably like a left, right, left. You have to do 3 different numbers, and it says repetition is not allowed. So I'm going to do this using the counting principle. There's going to be a first number that I need to pick, a second number that I need to pick, and a third number that I need to pick. For the first number, I can pick any one of the 31 numbers, numbers 1 through 30 and 0. Because it says repetition isn't allowed, for each subsequent number I need to go down by 1. So once a number is picked, I can't pick it again. So for the second choice, there's only 30 numbers left, and for the third choice, there's 29 numbers left. So I get 26,970 for the answer to 26. Social Security number has 9 digits, and we allowed repetition. So digits include just the numbers 0 through 9. There's 10 digits. So I need 7. I need 9 different spots. I don't really need to write numbers. First number, second number, all the way to the 9th number in the Social Security. And for each of these 9 numbers in the Social Security, it says repetition is allowed. So the numbers 1 through 9 and 0 are allowed each time. So it's just going to be 10 each time. And when you multiply with tens, it's easy to do. This is going to be a 1 followed by 9 zeros. I'll try to do that on my calculator and get 1 billion. So there's 1 billion different Social Security numbers that are possible. And once the population of the United States goes over 1 billion, well, then we have to have different Social Security numbers. Otherwise, multiple people will have the same Social Security number. And this is why I'm pretty sure if somebody dies, they give away their Social Security number again at some point in the future. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a 1 followed by 9 zeros. Assuming I did it right. Yeah, it looks like 1 followed by 9 zeros. It gets ridiculous when you start getting all the zeros. It's hard to copy the numbers even. Identification codes. The identification codes consist of 2 letters followed by 4 digits, means the numbers 0 through 9, the 10 different numbers. Okay, so for the first letter, it must be an A or an E. So there's only 2 choices for the first letter. Repetition is not permitted. There's generally 26 letters to choose from. I've used one of the 26 letters. I only have 25 left. The first number must be a 1, so for the first number there's 1 choice. And then for the subsequent numbers, I'm not allowed to repeat, so I go down. For the first digit, the second digit, I've used the number 1. There's 9 digits remaining, and then I'm not allowed to repeat, so I go down by 1, and I go down by 1. So let me try to do that on my calculator. So 2 times 25 times 1 times 9 times 8 times 7. That's going to give me 25,200 different codes that are possible with those criteria. Having 2 letters followed by 4 digits, digits being numbers 0 through 9, which are 10 of them, and the first letter being an A or an E, first number being a 1, and repetition not allowed. So, again, I'm going letter, letter, digit, 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 digit. It says repetition of numbers is not permitted, but repetition of letters is permitted, no other restrictions. So for each letter, there's going to be 26 letters to choose from because I'm allowed to do a double letter. But for the digits, I have to increment down 1 each time because I'm not allowed to use a digit more than once. And I get 3,407,040. Peppers. How many letters are in peppers, and then how many duplicates are there? So for this kind of permutation problem, the numerator, we form a fraction. The numerator gets the number of letters factorial. So there's 1, 2, 3, 4, 5, 6, 7 letters in peppers. So I get a 7 factorial. The denominator gets a factorial for each duplicate letter. For the peas, there's 3 of them. The denominator is going to get a 3 factorial. For the e's, there's 2 of them. The denominator is going to get a 2 factorial. There's only one r and one s, so I don't get a factorial for either of those. So I'm going to figure out what 7 factorial is, doing 7 math, going down to the number 4. So that's going to be 5,040. And then in the denominator, 3 factorial is 6. And 2 factorial is 2. So this is 5,040 divided by 6 times 2. I'm afraid I might mess this up. I'm going to go 5,040 divided by 12. I think I probably could just go 5,040 divided by 6 divided by 2. It'd probably give me the right answer, but I'm going to make sure that that actually works. And do 5,000. It does. So I could have just did divide. Regardless of if I cleaned up the denominator or not, you get 420 different ways to arrange the letters of the word peppers. So the stuff from 31 on is from sections 4.8 and 4.9, and check the syllabus to see if you have to do those. If you don't have to do those sections, then you're done with the review. If you have to do 4.8 and 4.9, then you need to do this part. So the rest of the problems are combination problems. On problem 31, you only have room for 8 new videos on whatever, your tablet, and you have 20 that you'd like to pick. How many different combinations of videos can you have? So I want to get, of the 20, I'm going to pick 8. The order that I pick them in doesn't matter, so it's a combination problem. So now I'm going to type the number 20, go to math, go over to PRB, and then pick the C1 and do 8. So there are 125,970 different groups of 8 videos you can pick from 20 videos. 32, how many 7s can be made from the 4 7s in a deck of cards? So from the 4 7s, I want to pick 3 of them. I'm assuming that order that I select them in isn't important, just the 3 7s that I pick are important. And that should be 4, because each time I pick a group, I'm missing 1. 4 math, probability, choose 3, and I get 4. Four members of a club will be selected for a conference. The club has 5 female and 8 male members. How many different groups can be selected with 1 male? So for the males, there's 3 males, and I need to pick 1 of them. For the females, the club has 5 females. I need to pick 3 of them. I need to do a combination for each. I need to do 1 of the 3 males and 3 of the 5 females. I'll do that on my calculator to confirm this, but I think it's going to be 30. 3 choose 1, I believe, is 3. 5 choose 3, I believe, is 10. So this is going to be 3 math, choose 1, which is 3, and 5 math, choose 3, which is 10. So it's 3 times 10, which is 30. Write your answer as a percent. So this is a probability question, so I want to have a fraction. And the numerator needs to be the desired characteristic. The denominator could be what can happen. So for the denominator, the class has 25 people, and I can pick any 4 of them. That's going to be a 25, choose 4. So I'm picking 4 of the 25 people. This class has 5 freshmen and 20 that are not freshmen. And I want to pick no freshmen, which means I want to pick 5 of the 20 that are not freshmen. So for the numerator, what I want is, of the 20 that are not freshmen, I need to pick all 4 of them. And that's going to be a 20 choose 4. So the numerator is what I want. I want to get 4 of the 20 non-freshmen. The denominator is what I could get. I can get 4 of any 25 people. So this is going to be 20 choose 4 over 25 choose 4. And I'm going to make that into a decimal and then to a percent and round to 1 decimal. So I can do this all at once if I want. I can go 20 math choose 4, close out a parentheses, hit a divide key, and then parentheses, 25 math choose 4, and I get 0.38300. Move the decimal over twice, that gives me 38.300%. Round to 1 decimal, it's going to be 38.3%. Two more, I think. One more, I think. So, a committee of 6 is going to be randomly selected from 7 teachers and 8 students. So, the denominator, what could happen, I'm selecting 6 from the 15-member committee, the 15-member group, 7 teachers and 8 students. So I can get any 15, I can get any 6 of the 15. What I want for the numerator is I want to get, for the teachers, I want to get 3 of the 7 teachers, and I want to get 3 of the 8 students. So my numerator is going to be a combination of 7 choose 3 times a combination of 8 choose 3, and my denominator is going to be a combination of 15 choose 6. I'll do each one of these separately. So I'm going to do 7 math choose 3, which is 35, and then 8 math choose 3, which is 56, and then the denominator 15 math choose 6. So now I need to do 35 times 56 divided by 5005. So 35 times 56 divided by 5005. That's 0.39160. Move the decimal over twice. That gives me 39.160%. Asked me to round to 1 decimal place. That 6 is going to round that 1 up to a 2. I'm going to write 39.2%. So 39.2% is the probability that we get 3 students and 3 teachers on that committee. So that should be everything. Again, make sure to see if you're required to do sections 4.8 and 4.9. If you are, then the last few problems are for you. If not, then you don't have to worry about those.